Good evening, everybody. Tonight we're seeking positive integer ordered pair solutions to this radical equation with two unknowns. And y'all, the positive integers are sometimes referred to as z plus. Okay, we know zero's not allowed, or nor the negative integers. Okay, so this is the positive integers cross Cartesian product with the positive integers. Okay, and again, there's two unknowns here. Now, there's a very natural substitution. Just if you look at the way this is set up, we have x plus 5 occurring twice in the radical, and also 32 minus y. So these substitutions are quite natural and to be expected on a problem like this. If you just tried to square away, it would be fairly messy, maybe intractable. Okay, so what we get now with these substitutions, u and w, this part right here, this left-hand side, or this entire equation, just becomes uw minus 3u plus 7w equals 34. And that's still not much fun. Now, all we've done is just change the names of things, but we still have one equation and two unknowns. Now, let's go ahead and make a couple of observations. We know that both u and w have to be greater than or equal to 0, which turns out to be quite important later on. Remember, the range of the square root function is non-negative real numbers. Also right here, same for w. So w is greater than or equal to 0. Okay. Now this next step perhaps is the most unnatural step in the entire problem, but the motivation behind it is that if you subtract 21 from both sides, you actually get a common binomial factor here. W minus 3 times w minus 3. The 13 comes from the fact that you had to subtract this 21 from the right-hand side. So 21 deducted from 34 gives you the 13 you see right here. That turns out to be useful because it's a prime number and we don't have to look at that many factor pairs. Now, again, folks, let's just take a look at the factor pair 1 and 13. Okay, if you associate 1 with the factor w minus 3 and 13 with the factor u plus 7, that certainly implies that w is equal to 4. Okay, y'all, this is just by inspection. If you again, 13 has just two, 1 and 13 are the only divisors of 13. It's a prime number. Okay, so that gives you w is equal to 4, and u must be equal to 6. Okay, so u has to equal to 6. Okay, now it's tempting to think you're done here, but really you have to look at all possible products. Like, for example, what if you did 13 here? You can reverse the factors, right? 13 and 1. Okay, well, what would that tell you that w had to be? Okay, that would imply if 13 is equal to w minus 3, that would say that w is equal to 16, right? Okay, but what about if you set 1 equal to u plus 7, that would force u to equal to what, negative 6? So you see, we have to cross this out because remember, both of the expressions have to be non-negative. So you see, we can't use this. Now, it doesn't take much work to see. I'll go ahead and write this down, but I won't carry out. You get nothing but negative values if you do negative 1 times negative 13 and negative 13 times negative 1. Okay, these both lead to no solutions. Okay, both of these lead to no solutions. It's very easy to see that if you have nothing but negative numbers set equal to these expressions, you're going to get negative numbers back, or at least one negative number back, and have to reject it. Okay, so you reject all the solutions except w equals 4 and u equals 6. Okay. Again, y'all, I left out the work right here, but it's pretty easy to see that I think both w and u would be negative, or at least one of them would be negative in all of these, okay? So this is the only one that works and yields positive, it sticks to the domain restrictions here, okay? So let's keep going. Now, I just wrote down the work for you here for u equal to 6. See, we concluded u is equal to 6. If u is equal to 6, that forces x to be 31. That's very clear, right? If you square both sides, or just by inspection, right? 31 plus 5 is 36. Square root of 36 is 6. In a similar fashion, we get y is equal to 16. And so these are our only two solutions. only possible solutions. Now, it never hurts to check, right? So let's see what happens when we do check it. This is the original equation. So right here, you would get the square root. What do we have right here? If x is 31, this would be 36, right? So we have the square root of 36 times 16. All right. And again, folks, all I'm doing is taking these values of 31 and y and substituting right here. Now here we have minus 3 times the square root of 36. Right? Okay, and then plus 7 times the square root of 16. Now, again, to be fair, we're not saying it's equal to 34. We're asking a question, is it equal to 34, right? So let's see what happens right here. This would be 6 times 4, right? The properties of radicals would be 6 times 4. So that'd be 24 right here. 24 minus 3 times 6, well, that's minus 18, right? Minus 18 right here. And then plus 7 times 4, which is 28 back. All right. So does that work out? It sure does look like that's equal to 52. Let's see here. 28 plus 24 is 52, right? And so you get 52 minus 18, which is certainly equal to 34. So this does check. So we can check up on that. And folks, these are the two solutions, and we'll write it like the original problem said, was 31, comma 16 is the ordered pair solution. That is the answer to the question, ladies and gentlemen. By the way, I tried this on Wolfram Alpha, and it couldn't solve it. When you substitute this into some of the online equation solving pieces of software, it does not work. It just goes crazy. It doesn't get the correct answer at all. It doesn't even get close. So that's kind of interesting all by itself. But anyway, that does it. Let's see here. So our solution is 3116. Put up here. 31 comma 16. And that's it. Thank you guys for viewing.